All right, so good morning, everybody. We've got William H. Murray on the line and on the video, and Bill is going to be talking about the strength of materials. So, Professor, go ahead.
Last week, at the colloquium on information systems security in Orlando, I was reminded repeatedly how much computer security education owes to, and has yet to learn from, engineering education. For example, every engineering student takes a course called Strength of Materials. In this course, he learns not only the strength of those materials that he is most likely to use, but how to measure the strength of novel materials. The student studies how and in how many different ways his materials are likely to fail. He learns how to design in such a way as to compensate for the limitations of his materials. A computer science or computer security student can get an advanced degree without ever studying the strength of the components that he uses to build his systems. It may be obvious that not all encryption algorithms are of the same strength, but how about authentication mechanisms, operating systems, database managers, routers, firewalls, and communication protocols? Is it enough for us to simply know that some are preferred for certain applications? Courtney's first law, remember, that's the one that says nothing useful can be said about the security of a mechanism except in the context of a specific environment and application. In this construction, security is analogous to strength, environment to load or stress, and application to the consequences of failure. Said another way, environment equates to threat or load, and application to requirements. Computer science students are taught that their systems are deterministic, that integrity is binary, that security is 1 or 0, that they are either sound or broken. On the other hand, William Thomson, Lord Kelvin, cautioned that unless one can measure something, one cannot recognize its presence or its absence. W. Edwards Deming taught us that if we cannot measure it, we cannot improve it. One way to measure strength of a material is by destructive testing. The engineer applies work or stress to the material until it breaks or deforms, and measures the work required to break the material. Note that different properties of a material may be measured. The engineer may measure yield, compressive strength, impact, tensile, fatigue, strain, and deformation strength. The strength of a security mechanism can be expressed in terms of the amount of work required to overcome it. We routinely express the strength of encryption algorithms this way, that is, the cost of a brute force or exhaustive attack, but fail to do it for authentication mechanisms where it is equally applicable. As with engineering materials, security components may be measured for their ability to resist different kinds, for example, exhaustive or brute force, denial of service, dictionary, browsing, eavesdropping, spoofing, counterfeiting, asynchronous, or other kinds of attacks. While some of these attacks should be measured in cover time, the minimum time to complete an attack, most should be measured in terms of the cost to the attacker. Now, there are now a number of ways in the literature for measuring the cost of attack. The cost used should consider the value or cost to the attacker of such things as work, access, risk of punishment, special knowledge, and time to success. Since these are fungible, it helps to express them all in a similar metric like dollars, my favorite. Of course, we will never know these with the precision that we know how much work it takes to fracture steel, but we can measure them well enough to improve our designs. The Trusted Computer System Evaluation Criteria, the TC set, can be viewed as a primitive attempt at expressing the strength of a component composed of hardware and software. While an evaluation speaks to suitability for a threat environment, with few exceptions, it does not speak to the work required to overcome resistance. One such exception is in covert channel analysis, where the evaluation is expected to speak to the rate at which data might flow in such a channel. Because it is often misused, a caution about the TC-sec is necessary. The TC-sec uses divisions. The division in which a component is evaluated is not a measure of its strength. Many fragile components are evaluated in division A, while some of our strongest are in D. In order to understand the strength of a component, to understand how to use it, one must read the evaluation. We have two kinds of vulnerabilities in our components: fundamental limitations and implementation-induced flaws. The former are more easily measured than the latter. On the other hand, it is the implementation-induced that we are spending our resources on. We are not developing software as well as we do hardware. We're not developing it even as well as we know how. The engineers use their knowledge of the strength and limitations of their materials to make design choices. They use safety factor and margin of safety metrics to improve their designs. More recently, engineers at MIT's Draper Laboratory have proposed that, quote, complex systems inhabit a gray world of partial failure. Oliver DeVeck, associate professor of aeronautics and astronautics and engineering systems, says, quote, if you admit ahead of time that the system will spend most of its time in a degraded state, you make different design choices. You can end up with airplanes that look quite different because you're really emphasizing robustness over optimality. Said another way, systems may be optimized for operation over time rather than at a point in time. The more difficult it is to determine the state of a system at a point in time, the more applicable this design philosophy. Thus, we see organizations like NASA designing and operating their systems and networks under the assumption that there are hostile components in them. While most of our components are deterministic, none of our systems or applications are. They have multiple people in them and interact in diverse, complex, and unpredictable ways. Therefore, designing for degraded state may be more efficient over the life of a system than designing for optimum operation at a point in time. We should be designing our systems for fault tolerance and resilience. We should be designing to compensate for the limitations of our materials. Of course, I'm aware that this audience, my audience, of information assurance and law enforcement professionals cannot reform computer security education or practice. I will continue to advance that agenda in other forums. What I hope for is that you will spend some of your professional development hours, effort, and study on the idea of strength. Just go and read the section in Wikipedia on strength of materials. What I hope for is that this will inform and improve your practice. It is in part because our education is a work in progress that we are called professionals and are paid the big bucks. Joe, over to you.
Yeah, no, great talk, and what a great comparison too, right? To the engineering community, where we do depend on them and rely upon them in a lot of different ways to get it right all the time.
Their tradition goes back 2,000 years to when the Romans made the engineers stand under the bridge while the army marched across.
Yeah, well, there's proof positive, huh?
We call that having skin in the game.
Yeah, well, having skin in the game, and that's what you just brought out here, really having skin in the game, and getting the software developers to maybe even just get close to the hardware developers, and maybe getting the hardware developers closer to what the engineers would, probably insist on.
My heroes are the aeronautical engineers who put together millions of parts, load them up with fuel and baggage, and live passengers and operate them at 35,000 feet. They consistently do a better job than we do.
Yeah. Well, it's a good comparison out there, and it's certainly a goal for people to strive towards. So, great editorial once again, Bill. All right.